Okie dokie smokies. Welcome back to inverse trigonometry. Yay! Inverse trig. Boop! On Friday, we talked about inverse trig functions being used to cancel, well, not cancel, no, excuse me. We talked about inverse trig functions being used to figure out what angles give us side lengths. So to recap, sine, cosine, tangent of an angle always results, always results in a ratio of side lengths. Switching your input and your output, that's what inverses do, tells us sine, cosine, or tangent inverse of a ratio of side lengths always results in an angle. So we always want to keep that in mind. And we learned about their domain restrictions on sine, cosine, and tangent that were required in order to ensure that the inverses were also functions. And what we did then is we said for sine of x, we have to restrict its domain from negative pi over 2 to positive pi over 2. This way we pass the horizontal line test. This is the graph of sine inverse of x. Since sine of x's domain is from negative pi over 2 to positive pi over 2, which we're calling quadrant -1 and quadrant +1, sine inverse's range can only return values from quadrant -1 and quadrant +1. We did the same thing for cosine of x. We chopped it from here to here, so it would pass the horizontal line test. That was restricting cosine's domain to quadrants 1 and 2 from 0 to pi. And if the domain of cosine is from 0 to pi, the range of cosine inverse is 0 to pi. So we can only return values for cosine inverse from quadrants 1 and 2. And then lastly, tangent, much like sine, from negative pi over 2 to positive pi over 2. The difference is tangent doesn't exist at negative pi over 2 and positive pi over 2. So the range for tangent inverse is negative pi over 2 to positive pi over 2, but we'll never include those two because tangent is undefined at those two values. Therefore, there are horizontal asymptotes for tangent inverse. Interestingly, the domain for tangent inverse is all real numbers. That's not the case for sine and cosine inverses. Cosine inverse domain is from -1 to +1 because that's the range of cosine. And sine inverse range also -1 to +1 because that's the range for sine. It's a whole lot of recap. What is the purpose of an inverse function? The purpose of an inverse function is to essentially undo what a function does. So in less words, it cancels our function. And if you compose them, if you can remember all the way back, I think this is a topic 1 thing, unit 1 topic, something like that. If you compose a function and its inverse in either order, they should cancel each other, leaving you just the argument x. That would be the goal, right? All right. But that's only if they're true inverses without breaking each other's domain and range rules. I have to say something like that for trig and trig inverse. Now let me tell you what's going on here. You're seeing a function and its inverse cancel each other out. But here's the thing. That's only going to work as long as you play in the right quadrants for sine inverse. It's only going to work if you play in the right quadrants for cosine inverse. And it's only going to work if you play in the right quadrants for tangent inverse. These things do something rather unique because even though they're true inverses, they won't always instantly result in a cancellation and just give you back your argument. And you'll see what I mean by that. Now, I'll tell you what, there's a whole bunch of stuff in this table that you could try to memorize that I have none of that memorized. I just know that sine inverse can only give me back values of quadrants -1 and +1. Cosine inverse can only give me back values quadrants 1 and 2. And tangent inverse, just like sine inverse, is only going to be quadrant -1 and +1, not including the y-axis, so negative pi over 2 and positive pi over 2. I know that the input for trig inverse is always a ratio of sides, and I know the input for trig is an angle. And knowing those things makes it so that I have no idea what's under my hand right now. Okay? So, just using older knowledge and watching the rules as I go. So we're going to find the exact value, if it's even possible, of these. And what they are compositions of trig with trig inverse. Now, did we have to do sine and sine inverse? No. We could have mixed and matched trig with trig inverses. It doesn't matter which one you do. Sometimes it works, sometimes it doesn't. So, Mr. M, they're inverses. So the answer is 2 pi over 3. Well, not really. And here's why. Sine has no restrictions on where you evaluate it, right? Its input is an angle, and angles can be whatever they want to be. So where is this angle, 2 pi over 3 radians? Quadrant 2. So in order to evaluate this trigonometry, I would have to draw a triangle in quadrant 2, wouldn't I? Okay. And once I drew a triangle in quadrant 2, could I then use that triangle to do sine inverse? No, because sine inverse does not play in quadrant 2. So what we're going to do is, we're going to evaluate the argument of sine inverse first, and then go from there. We know this angle happens in quadrant 2. I'm going to draw that angle in quadrant 2. Picture not drawn to scale. They never are. Like so. It is an over 3. So what's the size of its reference angle? 60 degrees. Good. Because 180 divided by 3 is 60. So yeah, it's a 60-degree reference angle. This is a 30, 60, 90 right triangle then. The side length across from a 60-degree angle is always either root 3 or negative root 3. I'm in quadrant 2 where y is positive, so it's root 3. That makes this the 30, which makes the side across from it the length of 1, but I'm in quadrant 2, so it's negative 1. And the hypotenuse slash radius is 2. What is sine of this theta? What is y over r going to get me? Square root of 3 over 2, root 3 over 2. So what this question actually says is, what is the sine inverse of root 3 over 2? And now, it's what we did Friday. This doesn't matter anymore. Which quadrant am I going to draw these side lengths in so that y is positive? Sine inverse, let's be playing which two quadrants, guys? 1 and negative 1, so where do I draw that? Quadrant 1. Good. So I'm going to draw it in quadrant 1. My y over r is root 3 over 2. That makes this a 1. So the size of this reference angle, we've already said there's always a 60-degree angle across from a root 3. I'm in quadrant 1, so 60 degrees in radians is, what is it? Pi over 3 radians. So there's your final answer. So no, they don't just instantly compose and cancel each other out because this one was in the wrong playground. So what does trig inverse do? Because trig inverse functions have restricted ranges, what they do is they'll take a triangle and reflect that triangle into an appropriate quadrant. See, sine is everywhere. Sine inverse is only quadrants 1 and negative 1. So it took this triangle and did this. Boink! And it reflected it into quadrant 1 where sine is still positive. And then gave us that angle. And if you type it on a calculator, it works. I did it in period 2 just to show you. There it is. So pi over 3 is about 1.05. There's the question we just did, and it returned about 1.05. So it did give me back pi over 3. So yeah, sine and sine inverse, they are true inverse functions. But because of restricted domains and ranges, they don't just give you back the argument instantly. They make us think just a little bit more. Still, I love these kinds of questions. I feel like they're a lot of fun. feels kind of like a math scavenger hunt, you know? This leads me to here, and then that leads me to there, and things like that. X marks the spot. Yeah, I don't know. I think that that's just a coincidence. I don't know. Maybe it's not. Who knows? Yeah, you go back and ask the pirates. Oh, no, it is a math poster. It's like find X, and it's a meme, and it's a kid on a math test, and they draw it with an arrow, and it says it's right there. Yeah. But anyway, hold on. We get back on track. Okay. So cosine inverse of 3 pi over 4. Where am I going to draw that? Quadrant 2. Everybody cool with that? Okay. So let me go ahead and draw this in quadrant 2. And its reference angle is what? A 45-degree reference angle. That makes this a 1, 1 root 2. But because of where I am, that's obviously that. Now, what is cosine inverse going to get me in this triangle? What in the world is happening at my door? Why? All right. I don't remember what I was saying before they pounded on the door. But, oh, I know. So I said, what is cosine inverse going to get me in this triangle? But how can it give me 3 pi over 4 if I... But this is 3 pi over 4. I'm confused. Remember me telling you that there was a question here that nobody caught was a trick? This question is not possible. But why? What is the input of all trig inverse? Side lengths. This is not an angle. These are side lengths of 3 pi and 4. That means a horizontal side of the triangle that's over 9 and a hypotenuse that's 4. That's not possible. You can't do cosine inverse of 3 pi over 4. That was just like this question that we saw on Friday. Remember, the input of all inverse trig is side lengths. So side lengths of 3 pi and 4 are not possible if 4 is the hypotenuse. This is undefined. And I didn't test that one on the graphing calculator, but for funsies, we might as well, just to see it say undefined. I'm going to put it back in radian mode, though. Hold on a second. Okay. So cosine inverse of the cosine of 7 pi... Wait, I'm typing the wrong question. Cosine of the cosine inverse of 3 pi over 4. And it should say domain error. There it is. Because you tried to violate the domain of cosine inverse.
Is it over 1?
Well, no, what it's saying is, it's because this number is bigger than 1, that's why. 3 pi divided by 4 is 2 and change, so it's bigger than 1. Yep, so we're undefined. All right, guys, next. That's the only trick question of the lesson. Next, cosine of. That means its argument is an angle. Yes, I can evaluate cosine at any angle I want. I just need to know where to draw this triangle. What quadrant? Quadrant.
No. Sorry.
3. 7 over 6 is bigger than 1 pi. Okay, this is quadrant 3. Does cosine inverse play in quadrant 3? No, it does not, but that's okay. So we're going to scavenger hunt our way there. So we draw quadrant 3. Over 6 is what kind of reference angle? 30. A 30-degree reference angle. We know that because 180 over 6 is 30. We've already mentioned it, but I'm going to say it again. Across from an angle of 30 degrees would be a side length of 1. I'm in quadrant 3, so it's negative. That makes this a 60, and across from a 60 is a side length of root 3. I'm in quadrant 3, so it's negative. And then that's a 2 because it's a 30, 60, 90. What is cosine in this triangle? Negative root 3 over 2. So this actually says, what is the cosine inverse of negative root 3 over 2? So where would I have to draw this triangle in order for cosine inverse to be able to play with it? Well, that's sine and tangent. Where's cosine first negative? Which quadrant? In quadrant 2. And that's why we have to reflect it up to quadrant 2. Not to here, but reflect it up into quadrant 2. It goes boink! And I can get the same cosine value from this triangle. It's still a 30-degree reference angle. And 30 degrees in radians is pi over 6. So if I am a pi over 6 away from this pi, what is my final result? 5 pi over 6. Again, the trig inverse will take a triangle out of a no-no quadrant and reflect it into a yes-yes quadrant. Okay? So this one, this trig inverse reflected it out of quadrant 2 to quadrant 1 because sine gets the same value in those two quadrants. This one reflected it out of quadrant 3 into quadrant 2 because cosine gets the same value in those two quadrants. Isn't that neat? Now what I find to be even more fun is when you compose different kinds of trig and trig inverse. I think this is more interesting. But I will say, though, I feel like the notes are a little bit remiss because there were no examples of trig inverse of trig with different functions. It is possible to do, but as long as you're comfortable drawing the shapes, you're fine. It's not a big deal. Alrighty, argument of trig inverse, its inputs are always side lengths. These are possible side lengths of a triangle in trigonometry. So, okay, bye. No, okay, so what quadrant am I going to draw this in? Quadrant negative 1, good. So this will be negative pi over 2 to positive, or to 0. I was going to say positive 0, like that. So we draw this triangle, picture not drawn to scale, it never is. And we fill out our side lengths. Sine is y over r. R can't be negative. That makes the 1 the negative. That makes this a root 3. And guess what? We don't even care. Wait, did I mess something up? It's what? Oh, stop it. This guy. Anyway. My triangle is drunk, okay? So anyway, even though I know what theta is, and we do know what theta is because this is clearly a special right triangle, you don't care. You don't need to know what that theta was. Look, I'll prove it. What is cosine here? Cosine. Root 3 over 2. Cosine's x over r. It's root 3 over 2. Notice I didn't even need to know that theta was negative pi over 6 radians. I could say it, but it wasn't necessary because I drew this triangle and then said, what's cosine in that triangle? Never caring what theta was. Which is kind of cool. What's that? So anytime you're doing trig of trig inverse in that order specific, you'll draw one triangle that the trig inverse forced, and then you'll use that one triangle. It's when they're swapped. So if you come back over here, you'll notice the difference was these started with trig inverse. That's what's going to force you to draw two triangles sometimes. So if and I don't want you trying to memorize that. It just ends up being a pattern that you get used to seeing, that you know the outside is restrictive. So the inside might force you to go somewhere you didn't want to be. But In this one, you go where it told you to and then just evaluate some trig, because you can evaluate trigonometry everywhere. Tangent every now and then will be undefined. But other than that, who cares? Okay. So, cosine inverse being positive, cosine inverse's argument being positive, forces us to draw a triangle where? First quadrant, because in quadrant 2, which is the only other place where cosine inverse could have played, x's would have been negative. So clearly we have a right triangle in quadrant 1, and the x over r gets us 5 over 13. How do you find a missing side of a right triangle? The Pythagorean theorem. X squared plus y squared equals r squared. Awesome. 25 plus y squared equals 169. You subtract 25 from both sides, you get y squared is 144. And since we are in quadrant 1, we know y is positive. Dose, 12. Okay, we throw 12 on this triangle. Who cares what theta is? By the way, it's not one of our special right triangles. Who cares what theta is? What is sine at this theta? 12 over 13. That's it. So we were able to do that without ever knowing theta, which is pretty cool. So 2 different times now, we've composed trig with trig inverse and did not know what theta was. Because of this, mathematicians a long time ago realized that means if you compose trig with trig inverse in the correct order, you can hop over needing to know that theta and then just use the argument of the trig inverse. So what we're going to do here is write a function that once you know the input of the trig inverse, you can spit out a value at the very end without ever knowing the angle in between. So cosine inverse. Which 2 quadrants can cosine inverse exist in? 1 and 2. Now this one specifically says x is positive. Okay? So it puts us in quadrant 1. However, just so you know, it wouldn't matter, because we're going to do sine of the resulting triangle, yes? And if I had drawn a triangle in either quadrant 1 or 2, they both would have positive y values, which means the sine in that triangle would have been positive regardless. Are you comfortable with that idea? Cool. Awesome sauce. What do we know? We know the inputs of trig inverse are side lengths. So this needs to be the ratio of side lengths. It must be a fraction. What is its denominator? Psst. Shh. What is the denominator? The way it sits right now, what's its denominator? 1. The denominator is 1. All right. That puts an x here, and it puts a 1 here. How do we find missing sides of a right triangle? Pythagorean theorem. Oh, okay. So we have x squared plus y squared equals r squared. Our x is x, so we have x squared plus y squared. Our r is 1. And we're trying to figure out what y is because I'm going to have to do sine. So that's going to be y over r. I need to know y. I do know it's positive, though, because if I'm either in quadrant 1 or negative 1, or excuse me, 1 or 2, sorry. And in both quadrants, y is positive, so nobody cares. So it did say x had to be positive, though, so it forces me here. So I know y is positive. I subtract x squared from both sides. And take the square root of both sides. If we hadn't been told that x was positive, would it have made it a plus or a minus situation? Nope. No, because cosine inverse can only draw triangles in quadrant 1 and 2, and y is positive in both of those. Okay? Oh, I know my y value. My y value is the square root of 1 minus x squared Ta-da. And I don't know theta. Oh, theta's already there. I was about to draw it in red. I don't know theta, but I do know that this is the triangle around it. And what is sine in this triangle? Square root of 1 minus x squared. Yep. It's y over r. Ta-da! So just to prove a point, let's use our formula that we just created for this one. And let's show that it equals this. So we got this 5 over 13, right? I'm saying that if you use 5 over 13 right here, you should get that. Second square root of 1 minus 5 divided by 13 squared is, eek! 12 divided by 13 is that. So it worked. So we have a function that hops right over knowing theta and composes for you and gives you its result. Yes?
To find from cosine, from inverse sine, would you just do...
Wait. So if it said cosine of sine inverse?
Would you just do 1 minus y squared?
Yeah, it'd be 1 minus y squared, yeah. But typically we just say x is the input x, so you'd still use an x. So that would be angle x, not... It would be unknown side length x, regardless of whether or not it's a horizontal or a vertical. We're just using x as an unknown in that point, okay? It's just variable x, not specifically the vertical x. Cool? And a word problem. Kinda. A modeling question. An airplane flies at an altitude of 5 miles towards a point that is directly over your house. We have an image like this. It says write theta as a function of x. Okay, well, check it out. How can I relate these two sides to each other at this theta? Tangent. From this theta, this is the opposite and this is the adjacent. So what we know is that tangent of theta is 5 over x. It says write theta as a function of x. That means get theta alone. How? What gets theta alone? Inverse of tangent. So tangent inverse of both sides. Ta-da. So it says figure out the angle when the airplane is 8 miles from the house horizontally. So you just plug in x equals 8. So theta is the tangent inverse of 5 over 8. I'm in radian mode. Oh yeah, you can't. That's not a special right triangle, so you have to use a calculator. Second tangent of 5 divided by 8 is that number, about 0.559 radians, which doesn't really mean much to most people. Most people think in degrees. So let's get it in degrees. Mode, degree, and I don't feel like typing it again, so I'm just going to go up and hit enter, and then enter. There it is. About 32 degrees. To 3 decimals, it's 32.005 degrees. Ta-da! Questions, comments, concerns, nerds? Oh, yes, Mark.
0.559 radians.
Yes.
So that means it's pi, right?
0.559 radians. That means something times pi equals 0.559. It's not a fraction of pi. It's just a number of radians. Okay. Yes, Adi? Is there a reason why there's not what? Why there's no tangent examples? No, there just isn't. As long as you know where to draw because of tangent inverse. Yeah, that's just to keep the notes shorter. Yep. Nope, nothing special happens. As long as you can draw your triangles appropriately and where they go and things like that. And watch out, input of trig inverse is always side lengths, you're gonna be set. I think you nerds are ready to rock and roll. Thank you.